Thanks, Davo. Well, first of all, I want to thank the organising committee for the opportunity to talk on a subject which I suppose you'd say is not my core business, but something very dear to my heart, which is electronics. And I hope you'll find it interesting. For those of you who are electronic engineers or physicists, all I can say is a little inaccuracy will save a tremendous amount of explanation. We've got a lot to cover. I think it would be best if we leave questions until the end. So what I want to talk about tonight is the second industrial revolution, which the first one being replacement of muscles, the second one replacement of brains. And one of the funny things about revolutions is you usually don't know they're happening until they're over, and then you look back, because the steps that are involved are often quite small. So we just think about all these topics that I've listed here, which will involve us in our everyday life. The thing which is common to them all is that they all depend on electronics and on computer chips. And you might be surprised to find that in 2021, the average car had about 1,200 chips, and that figure has doubled since 2010, and it's likely to increase. It's actually a significant fraction of the cost of a car now. So I want to deal with just 4 topics. First of all, what is a semiconductor? Secondly, how transistors work, how do silicon chips work, and how are they made? So let's start in December 1947, when the critical experiment was done in Bell Labs, and the first working transistor, which is what is known as a point contact transistor. And what you can see here is a lump of germanium crystal. And we have a triangular piece of plastic and 2 sheets of gold leaf, which are bent around the corner here, and a tiny little cut was made with a razor blade, so that these are now 2 separate electrodes, but very, very closely spaced, which was very important. And of course, you can see the paperclip up the top. Now, that was 1947. 1958, so it's a significant delay, transistors were starting to be commercially produced. And this one is an early one made with germanium, OC71, and cost £5. I remember my father bringing one home in his sports coat pocket. Here you can see an early integrated circuit. This is the legendary 555, which is a timer chip in 1971. What I've done here is to put it in the vise in the workshop, and with a file, I filed off the top, and I was scared that I was going to damage the chip, but you can see the chip is actually still there. And if we look, that chip in 1971, state of the art, has 23 transistors and a bunch of other parts. And here I've put it under microscope. You can see a normal pin, and you get a bit of an idea. The chip's probably about 1 millimeter in each side. And here is high power view. It's amazing with the rough treatment that it got that you can actually see anything at all, but you can actually see the number 555 etched on this silicon chip. Amazingly, still about 1 billion of these are sold every year, even though it's 1971, it was a particularly good design, and you probably have one in your toaster. Just remember the word toaster, because we'll return to toasters. So what was the driving force that led to transistors and integrated circuits? Well, it all began with telephones. And so, of course, it was done in Bell Laboratories. And Bell Laboratories, as the telephone became more and more popular, had a problem with switching. They were getting too many subscribers, And the question was, how could you connect them all up? And this was a telephone exchange in Melbourne, 1884. And you can see these ladies who would use a plug to connect everything manually. Here's a telephone exchange up to about the 1970s, or maybe a little bit longer, from the Telstra Museum in Melbourne. And what you can see here is these are called uniselectors. And uniselectors are a mechanical sort of form of relay. And when you dial the telephone, the little arm here rotates and it goes click, 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 click. So if you have a dial telephone, you dial 5, you'll hear 5 clicks and the arm will move around 5 spaces and basically it will connect. I have one here to demonstrate and afterwards you can play with it. But the important thing is wires absolutely everywhere and it's incredibly noisy. Here is a telephone exchange. Now, that's just one bank of uniselectors. And if you imagine thousands of them all going at once, the noise would be deafening. So let's have now look in a bit more detail. And we're back to the 1947 experiment with the prototype transistor, which I said is called point contact transistor because of these points touching the germanium crystal. The amazing thing is we still don't fully understand how it works. Here we can see the 3 inventors. There's Bill Shockley in the center, John Bardeen on the left, and Walter Brattain on the right. Now, this was taken as a recreation in 1948, and Shockley was the boss, but he was actually out of town when the critical experiment was done, and so the attorneys felt that he really didn't have a role to play and shouldn't actually be on the patent. He was extremely annoyed about that. The others were very annoyed of having him center stage when they really didn't deserve it. Shockley was a brilliant man, but he had a rather flawed personality. He had perhaps what you'd say lacked people skills, and we'll see some examples of that as we go through. But the result was 1956, the 3 of them got the joint Nobel Prize. Now, getting 1 Nobel Prize is a very big deal. So it was just that one time you got a Nobel, was it? Well, in fact, John Bardeen got 2 Nobel Prizes in physics. He's the only person who's ever got 2 Nobel Prizes in physics, and one for 1956 for semiconductors, the second one for superconductor, understanding the theory of superconductors. He was a very modest man that said that he played golf with his friend for years and years, and after the second Nobel, his friend said, well, John, what do you actually do? Let's now have a look at what are conductors, insulators, and semiconductors. So this will be something all of you know, I assume, but for those, perhaps if there are any children in the audience, an electric current is due to the movement of electrons. And the other thing you need to know is that like charges repel each other, unlike charges attract each other. And we can actually understand it reasonably well with just high school chemistry and physics. So a conductor is something where the electrons move freely, say copper or aluminium. Insulators, the electrons can't move. And the critical thing here for now is glass is an excellent insulator, and glass is just silicon dioxide. And semiconductors are very strange, and we'll see how they are strange and how they work in a moment. but silicon and germanium are the two that are of interest. The first transistors were made of germanium. Later on, silicon was preferred. And the resistance of semiconductors can be controlled by doping with small, very, very tiny amounts of impurities. And the reason why there was a lot of trouble in understanding them was because different samples had different conductivity. But if you got them very pure, then silicon does not conduct at all. But it has, when I say very pure, it has to be 99.9999999, I think I've got the number of nines right, percent pure. But if we just put in a few parts per million of impurities, then it can conduct. And the important thing is we're going to deal with phosphorus, which generates a few extra electrons, which we call negative charge carrier. So the electron carries the charge in a current, but a boron generates holes, and holes can act as positive charge carriers. And that is a bit of a mouthful. So what does that actually mean? Well, we'll have to go to the periodic table, which I hope you'll all remember that here we have the Bohr-Rutherford model of an atom, and the innermost shell has a maximum of 2 electrons. The next shell out can have a maximum of 8. And when the shells are full, the situation is very stable. So here we have hydrogen, second element helium, so the inner shell is full, so that's an inert gas, very stable. Then we go down element 3, lithium, beryllium, and then we get to boron, which has 3 electrons in the outer shell. Carbon has 4, and so we go through to 8 with neon, which is also an inert gas because the stable nature of having that inner shell full. Then we get down to the next row, and you'll see we have element 14 is silicon, and then the next one along is phosphorus. And what we'll see is that boron has 3 electrons in the outermost shell, silicon has 4, and phosphorus has 5. And then if we can continue here, we get to 8 and argon once again in inert gas. So let's have a look at the silicon atom. And you can see here the 4 outer shell or valency electrons. But if we look at the silicon crystal, the situation is quite different, because in a crystal, you get sharing between the different silicon atoms, such that each silicon is actually surrounded by 8 electrons. And so that's a very stable situation. And in fact, the electrons, they're very tightly bound, and the silicon, if it's very pure, will not conduct. But if we introduce tiny amounts of phosphorus, we have a situation where now the phosphorus can actually fit into the crystal quite well, and we have an extra electron, which can't be shared with the other atoms, and so it's free to move. And so this is what we call an N-type silicon, a negative type silicon, because it has free electrons. So that conducts very well. On the other hand, a situation which is more difficult to understand is if we have boron instead of phosphorus. And here we have boron atom, which has 3 electrons in the outermost shell. And what we have instead is a hole, because there's an electron missing. And so the amazing thing is that holes can move through a crystal, and they can act as a positive charge carrier. Difficult concept to grasp, but if we think about a parking lot here, we've got on the left-hand side a parking lot where we have a vacant space, and supposing this car on the left of the vacant space moves, what happens now is we have created a hole and filled the hole. The sort of hole has been annihilated by the movement of an electron. So this was Shockley's model, which I think is quite an easy way to understand movement of holes and electrons. Now, I mentioned that Shockley was very annoyed to be out of town and not getting the credit, and he went away and holed himself up in a hotel room and spent some time understanding the theory of what was going on, and he came up with a much better design for a transistor, which is called a junction transistor. And you can see here there's one type which has a layer of p-type silicon, layer of N, and then a layer of P, so PNP transistor. And these electrodes are called the emitter, base, and collector. You can have the reverse, an NPN transistor. So he worked all that out in theory, and after a fairly short period of time, it was possible to demonstrate that it actually worked, and it worked very well. And that was really the basis for transistors, for commercial transistors, for the next 20 or 30 years, until eventually they got superseded by a completely different type of transistor, which we'll come to shortly, field effect transistor. We now need to shift gears and talk about computers and numbers. So you can see here, have to get with it. This is the world of ones and zeros. Well, if we think about the real world, human senses are basically smooth. They depend on a continuous gradation of senses, and there are no real gaps. But so if we think of vision, or if we think of sound, that's the sort of thing we expect to see. But in the digital world, first of all, digital means fingers. And so we've got 10 fingers, and we'll see that's significant in a moment. So digits are ideal for counting. You know, children will learn to count on their fingers. But the digital world is actually not that new, because we think about it's just 1 or 0, on or off. So Morse code is an example of a digital communication. Now, the human world and the digital world don't really intuitively work well together. So in anything to do with computing, there will be a digital to analog converter, an analog to digital converter, so to allow these worlds to speak to each other. But those converters are very complicated, and we don't have time to talk about them, just take it for granted that they exist. But one thing that we should point out is that analog, which I'm not going to talk about today, is the real world, the world of sound and vision. And many people think, oh, analog is old-fashioned, but designing analog chips is in fact requires a great deal more finesse than designing digital chips. And the guru is Bob Widlar, who said any idiot can count to 1. So let's have a look at numbers. Well, as I said, the reason why we count in tens is because we've got 10 fingers. And for number 13, we have a 1 in the tens column and 3 in the units column. But the ancient Sumerians, believe it or not, counted in 60s. So the first column is singles, the second column is 60s, the third column 3,600s. And We don't know, of course, exactly why they chose that. I suppose it was convenient in some ways, but we still have the remnants of that in our society now, because it's 60 seconds in a minute, 60 minutes in an hour, and 360 degrees in a circle. So we can see that's remained. But in the case of binary digits, which we call bits, and 8 bits is said to be 1 byte. So now the first column is units, the second's twos, the third's fours, the fourth's 8. So 8 plus 1 is, 8 plus 4 is 12, and 1 is 13. So that's the binary system. Now, the critical person here, the hero, it were two heroes. George Boole in 1847 invented a form of algebra which was very good at dealing with binary numbers with just a few simple logical operations like and or not. You could have a form of algebra which is called Boolean algebra. The other hero is Claude Shannon here, and in 1937 Claude Shannon unified the worlds of electronics and logic. And I'll show you how he did that in a moment. But the end result is apparent here in 1964. The very first integrated circuits on silicon chips became available. His preliminary specifications for a Fairchild chip in October 1964. And they called them planar epitaxial micrologic. So the world of logic and electronics converged. And here you can see some simple Boolean operations. The simplest one is not. So a not operation is if you've got a 0, then it converts it to a 1. If you've got a 1, converts it to a 0. Then the operation or would be if you've got a 1 and a 0, then the output is 1, and it doesn't matter which input it is. If you have both zeros, then you get 0 at the output. Now, there are more complicated operations, but that will illustrate the principle. If we have and, then if we have two 1s, we get 1. If we have a 1 and a 0, we get 0. A 0 and a 1, we get a 0. So we can translate that very nicely into electrical circuits. And here you can see the operation of and. We have two switches in series. And to get the current going, we have to have both of them turned on. So that would be and. On the other hand, if we have two switches in parallel, either one, if we turn either one on, then the current will flow. Now, there, of course, you might ask, well, what happens if you turn them both on? But we don't have time to go into that. Now, let's now turn to how we can control the current. And here we have a pipe with, let's say, fluid going through it, and we call that a valve. With an electronic valve, which the Americans will call tubes, then it can control the current through a vacuum with a grid in between the two electrodes. And the big problem with valves, which became very apparent in the 1940s, is that they're bulky, unreliable, they generate lots of heat, and they're expensive. One of the biggest computers made using valves was ENIAC. It had 18,000 valves, and it was out of action a lot of the time because there would always be one which has failed. So it became apparent that there was a limit to how big you could build a computer. But of course, valves have a cult following now, and you can see that there's some people who think that valves generate the valve sound. I don't believe a word of it. But the important thing for now is that 99% of transistors are actually used as switches. The other 1% are used in analog circuits like hi-fi amplifiers, and we don't We're not going to talk about them today. Now here you can see that we get back to our telephone exchange and we've got a problem. And so it was still in the 1970s that still the mechanical exchanges were the norm. But now we have a new form of transistor that came along in the 1970s called field effect transistor, which had been patented in the 1930s by Lilienfeld, but it's not clear if he ever got one, a working model. He certainly understood the theory, the idea, but it turned out to be extremely difficult to actually reduce that to practice. And the person who did it first was Muhammad Atalla in Bell Labs in 1959. And they were very reliable, low power consumption, and most transistors these days are field effect transistors. And I want to show you how a field effect transistor works. And what you can see here is a field effect transistor with a crystal of P-type silicon. So lots of holes. There's still a few electrons, but mainly holes. And then we have two electrodes here, N-type silicon, one which we call the source, and the other one we call the drain. And then at the top is a very thin layer of silicon dioxide, which insulates the whole thing from the environment, and it also protects it against contaminants. And here we have a metal electrode, which is initially aluminium, but now often polysilicon, which we call the gate. And if we apply a positive voltage on the drain, what happens is that the holes, which are effectively positive charged, will be repelled from the drain. And so we end up with a little region here which has no charge carriers at all. So there's no conduction between the source and the drain. But if we apply a positive voltage on the gate, what happens is that now electrons are drawn from the N regions, and also some stray electrons, which we call minority carriers, will be drawn from the P region of silicon. And so now we end up with what's called an induced channel, where we have continuous region of N-type silicon, and so that will conduct. So what we have in effect here is a switch. Let's turn now to how transistors are made. Well, they're made in a foundry, and you all know what a foundry looks like. But that's not actually how a foundry looks for making transistors. This is a more accurate picture. It's all done on very small scale. So the first thing we need is ultra pure silicon. And the way it's done here is we have a furnace with some molten silicon, and we introduce a small silicon crystal and then gradually pull that crystal out of the what's called the melt. And so we end up growing a crystal of ultra pure silicon, and the impurities are left behind in the melt. And in that way, we can get extremely pure silicon. Here you can see the operation. And after we have this pure silicon crystal, then it's sliced up mechanically, and we have wafers. And wafers could be as much as a foot in diameter. And then the wafers are cut up mechanically into dice, or otherwise known as chips. And here we can see I've taken a transistor, it's in a metal can, and I've once again filed the top off it so that you can actually see inside this transistor. And what you can see is it's like a Rutherford atom. It's nearly all empty space. And if we look under higher power, you can see the chip here with a couple of the wires connecting to the chip. So that's what a transistor looks like. Now, Shockley then set up a company, Shockley Semiconductor, with the aim of producing transistors. But as I said, he lacked people skills and he didn't give credit where it was due. And ultimately, the company failed and he became a professor at Stanford and got obsessed with the idea that Africans had lower IQ than Caucasians. And of course, the big problem with that was that IQ tests are very culturally dependent. And basically, he went off on this silly tangent and ended up discrediting himself after he'd done excellent work. So the people in his company got fed up. And there was a group of them, 8, he called them the traitorous 8. And they decided, to hell with this, we'll go and form our own company, which was Fairchild. Fairchild was a subsidiary of a larger company, which was willing to fund this new venture. And there are just 3 individuals I want to point out here. On the very left is Gordon Moore, the founder of Intel, as we'll see in a moment. Robert Noyce, who invented the integrated circuit, was also a founder of Intel, and Jean Hoerni, who developed a planar process, which was essential, and we'll see that in a moment. So Hoerni's great insight was that here we have a lump of silicon, in this case it's P-type silicon, and he's generated a diode with just a junction between N-type silicon and P-type silicon. And the way he did it was to have a layer of silicon dioxide on the top, which protected the interior from contamination, which is extremely important because that was the key to having it very, very reliable. Then if you etch out a hole in the silicon dioxide, you can then diffuse in either P or N-type impurities, and then you can oxidize the surface again. And so now you've got a junction which is extremely stable. It's isolated from any contamination and it functions extremely well. And prior to that, people thought the glass was prone to contamination and should be removed. But what he established was that the glass was actually important to protect the junction, and these transistors made in this way worked extremely well. Here you can see the very first planar transistor, and you can see how different it is from the original junction transistor, but you can also see there's little specks. And so if you're going to make them on a very small scale, you had to have ultra clean, dust-free conditions. So the planar process was absolutely central. And here we can see the planar process in a little bit more detail, where we have this layer of P-type silicon, and then there's this glassy layer on the top of silicon dioxide, and then it was coated with a special photographic emulsion called photoresist. And this type of photoresist, if you shine light on it, then you could digest away the protective layer and expose the silicon. Then you could diffuse in the contaminants or the dopants, and then you could close the whole thing up again. And so what we've now got is essentially a photographic process for making a transistor. Now, what Bob Noyce's great idea was that if you can put one transistor on a chip, why can't you put 2? And so he filed a patent for doing that, showed that it could actually work. And the patent was in 30th of July, 1959, to just remember that date. then because we'll come back to it. And here you can see how integrated circuits are actually made, where we have a light source, a lens, we have what's called a mask, which was originally cut out by hand. Here's an example of a mask which will protect certain parts of the silicon and allow other parts to be etched away. And so you can see here that you can generate this little photographic image. You just step the wafer sideways, and so that you get thousands and thousands of replicas of the mask on a tiny, tiny scale. And here you can see one of the first integrated circuits, and it's got two transistors. This is actually a flip-flop, which would be regarded as a elementary memory device. And the important thing now is, instead of thinking of transistors, you think in terms of functions. And Fairchild then set up a company, did very well, and they actually set up a company in Melbourne, believe it or not, in Mount Dandenong, from 66 to 73. I used to drive up to Mount Dandenong and buy these integrated circuits directly from the factory, and here you can see one of them. Now, I mentioned 30th of July 1959. The reason for that is because in February 1959, another player, Jack Kilby in Texas Instruments, designed a similar idea. Here it's a germanium crystal, as it happens, then put two transistors on the one chip and joined them with these flying wires, and he patented it. And we're going to come back to that. Obviously generated a big problem in terms of patents. Now, the Fairchild employees, known as the Fairchildren, felt they were getting a raw deal and not getting a share of the profits, and things were going really well. So they decided, to hell with it, they're going to form another company. And Bob Widlar said in his exit interview, "I want to get rich." So Fairchild begat Intel, Integrated Electronics, and here we have the three key players. There's Andy Grove, Bob Noyce, and Gordon Moore. Each of them became famous in their own right. So the big problem with Intel is what's going to be their first product, and they had to identify a market. And now we need to just turn to the life cycle of technology. Things as state of the art become obsolete junk, and then they become collector's treasure. So here you can see the inside of a radio, 1948, and this is called rat's nest wiring for obvious reasons. By the 1950s, printed circuits became the norm. So this is a photographic process, a bit like what I just showed you. So that put a bit of order into things. But let's now turn to computer memories. So here we can see a computer memory which was used in computers right up till the 1970s. And this particular one I bought on eBay, came directly from Russia. It consists of 1,000 magnetic cores, and you can see them here. And each one's about 1 millimeter in diameter. I brought one along for you to have a look at. And each one has 3 or maybe 5 wires through it. And these had to be assembled by workers under a microscope. So you can imagine threading wires through 1,000 of these little donuts. What a tedious and slow process that would be. So that's the moon lander used memory of this sort. This one would store 1,000 bits, and the memory is non-volatile. And if we could read it, we could probably find out what was stored in it. So Intel's first product was silicon chip memory. This particular one, their first one, stored 64 bits. And what you can, so this took the world by storm. And so the donuts became just a memory. And that solved also the connectivity problem. So suddenly, instead of having a rat's nest of wires, you could join everything up and do it in an automated fashion very quickly, very cheaply. Now, Intel did very well initially, and things were going beautifully, but by 1985, just a short time, they got outcompeted by Japan, and they had to make this agonizing decision that they're going to get out of memories because the Japanese could make them more cheaply and more reliably. And so this was a heartbreaking decision. And what Andy Grove, who was the CEO, decided what you had to do is every few years, you've got to kill your children and reinvent yourself. So only the paranoid will survive. And the story about the microprocessor is quite an interesting one because there was a Japanese company called Busicom who subcontracted to Intel to make a pocket calculator. And so Intel would make the chip and it would be licensed to Busicom and they would own the rights to the chip. And then Busicom encountered their own problems of cash flow, and Intel negotiated with them to say, how about we'll sell you as many of them as you want, but can we have the rights as well? And then they very gradually realized that in fact the chip that was in the calculator could do anything at all. All you had to do is to program it. And so, as Andy Grove said, for the first 15 years, they didn't realize that the microprocessor gave it their future. And here is the first microprocessor, the 4004, which has about 2,000 transistors. The smallest feature is 10 microns, which is about the diameter of a red blood cell. And the mask for making it was actually cut by hand using color pencils to mark it out and a sharp razor to actually cut the mask. So let's now turn to Gordon Moore, the second of the famous people in Intel, and he has the famous Moore's law to his credit. Now, Davo will love this slide because it's a good example of data analysis. And what you can see here is that in 1965, he looked back and he realized that the number of transistors on a chip was doubling about every 2 years. And he then extrapolated that with just these few data points, that it would continue to double. But from here on, there was no more data. But that's what he predicted. And also that the cost would go down exponentially in the same manner. Now, astonishingly, the Moore's law has remained valid for 50 years. So I can't think of many other exponential processes that could go through that many doublings. But there's perhaps a self-fulfilling prophecy because people set that as a target. Here you can see that Moore's law was kept going all this time. Here are the actual original data points. And I'm sure he was probably as astonished as anyone to see that it continued right up until the 2000s. And it's now reached about the limit, as we'll see in a moment. So the advantage of being small is the cost goes down, the speed goes up, power consumption goes down, and so there's less heat, and they're very reliable. Incidentally, initially when people started making computers on chips, the question was, well, how do you repair them when they go wrong? The answer is you don't repair them, you throw them away. So the end of Moore's law is approaching because we're getting down to the very near the atomic level. Now, unfortunately, Noyce died in 1990 and Hoerni died in 1997. And so the Nobel Prize Committee finally decided this was worthy of a Nobel Prize, but by now the only one of them that was still alive was Jack Kilby with this very clunky model. And Kilby was a modest man. He realized he'd got the right idea, but the implementation was clunky and no one would make chips like this. So the planar process became universal. Now, I just want to finish up by saying, just giving you a few numbers. So the degree of purity that's required is absolutely astonishing. There are more transistors in the world than there are leaves on the trees and all the ants in the world. If you don't believe me, I can quote you chapter and verse. In 2015, the four main firms produced 14 trillion transistors per second. The cost of a transistor is now a millionth of a cent. And the current iPhone has 15 billion transistors in it. And here you can see the consequences of all of that. We start with the electromechanical switching, which was used in telephone exchanges up until about the 1970s, solid state relays, vacuum tubes held sway until the 1960s, I guess. The PDP-8 was the computer that I first learned how to program on, which is somewhere around about here, about 1968. Looked very primitive. It also had donut memory. And here we are at the present time, and it's a rather cheeky graph because it suggests that we might be approaching the mouse brain or the human brain in terms of power. And I just ask you to beware of your toaster because it just might answer back. Thank you very much.
So we've got some time for some questions, and once again, please join us for some refreshments afterwards, and then you'll have a greater chance to grill Jim. So, what was the Morse code that you were sending out there before?
Are there any radio hams in the audience? That's CQ, which stands for Seek You, and this is what the radio hams used to say if they want someone else to join in conversation.
This is before Tinder.
Yeah. I've been counting leaves and insects and that broadcast.
Well, I can't tell you how the calculations were done, but if you want to send me an email, I can get you the quotations, which are from people who I think we can trust their authority. It's mind-blowing, but I have no particular reason to doubt it. Oh, well, that's undergone tremendous changes. In the early days, it was visible light, and it gradually moved to shorter and shorter wavelengths because, of course, that's what you need if you're going to get smaller and smaller features. The current light source is a laser which uses tin to generate the light source, and the smallest feature now is apparently 2 nanometers. These lasers, I think, are extremely difficult to make. The main company that makes the foundries is a Dutch company that has virtually the monopoly, and very few other companies can compete at the very highest level. But you don't have to do all transistors using this super duper tin lasers. A lot of things can be done with a lower level of chip density.
Alan?
I think you were brave. You were very brave and in and that's quite collaborate. And I don't think you're going to be I guess this is what it's not.
Well, I think everyone is astonished, but when you get down to 2 nanometers, I mean, a nanometer is 10 to the minus 9 of a meter, and angstrom units 10 to the minus 10. So you're getting down to a few thousand atoms. So I guess you could build up. And so the next generation, I think, will be exploring all of those things. I'm certainly not an expert in what is happening in terms of trying to circumvent Moore's law, but it's obvious we can't just keep on making things smaller. One point that's worth making is that if you halve the feature dimensions, you actually can fit 4 times as many transistors on the chip because it's a square law, and so you gain a great deal by a small increase, small change in size. But no, I'm not the right person to ask about what's happening next.
Malcolm?
Already seeing AI putting towards an art, writing software, being able to do contracts, writing letters and like. Do you think the impact would be ultimately benign?
Well, once I was in a tutorial in medical school, and the professor of medicine said to one of the students, not to me, he said, "Well, Bloggs, you say that with such confidence that if I didn't know better, I'd almost be tempted to believe you." So we see these totally wrong answers given with great confidence. I think I found ChatGPT extremely useful, and a lot of the time it actually tells you what you want to know and gets it right. But I certainly think you need to check. Can you imagine a ChatGPT psychiatrist that sort of suggests that maybe it'd be a good idea for you to commit suicide? So you can think that you might need to build in some constraints and have to think about ethics and all kinds of things. So I think it's here to stay. I think it will probably replace Google for a lot of things. I'm astonished that it can actually master grammar and syntax and produce neatly ordered lists, things. It's very useful. So I think we've got to face the fact that, yes, we've got another revolution coming along, but better be careful.
With so many bits and pieces on a single chip, the probability of one of them not working is pretty high. How do you validate the integrity of the circuit?
Oh, right, a good question. Well, the first thing to say is in the early days, a lot of the chips were duds. And initially, you might have 1% yield, then gradually 10% yield. The thing which really improved the situation was improving the purity of the silicon and making better crystals. And so now the majority of chips will actually work, but each one has to be tested. And what you can sometimes do is to, if let's say it's a multi-core processor, if you've got, say, 6 cores and one of them's no good, you can just knock that one out and sell it at a cheaper price. So there are ways to deal with that problem. But overall, the reliability is extremely good. And if they work initially, they'll probably continue to work.
Enormous amount of effort because they're really each one is going through a validation.
Well, I think it's not. No, it's definitely not done mechanically. You'd actually have to test them electrically, and that can be done. Yeah.
I believe they can also have some, like, check some, parts, transistors that can check whether the rest of them are behaving. So you lose on the amount of memory that you've got, but some of the memory checks that it's operating normally and can inactivate or tell you to ignore those bits that are not.
There was a famous episode a few years ago with the Pentium chip, which had an error in it, and there's a cartoon of the Pentium chip ate my homework. So I think you'd be pretty lucky if you actually designed a chip and made it and got it working perfectly first go. These days, of course, the chips are actually designed by computer, and you don't draw the mask by hand anymore.
Yeah.
I do like the story you told about people who share a lot of parts. But I was thinking, what is that a parallel thing happening in Japan? It's just these few people making all these discoveries, and then I guess they picked up by everybody else. But that really was the few Americans who didn't try that.
Well, I think there was research effort going on in other countries, but I think really the epicenter was Silicon Valley. One interesting point was that there was a Japanese, ANZAAS, who got the Nobel Prize for designing a device called a tunnel diode, which gives extremely rapid switching. And it turns out that Bob Noyce had the same idea, and he'd sketched it in his notebooks, but he was busy with other things and he didn't pursue it.